So in this video, we're going to talk about the most often used derivative rule, and that is the power rule. So what we do if we have a power in or an exponent, right? So all of these are basically polynomials. Anytime we have a polynomial, that's pretty nice to use this power rule. So the first thing to do is if we're taking the derivative of a constant, right? The derivative of a constant is always 0. So anytime we have a number without a variable anywhere, then the derivative of that constant is 0 because the slope of a horizontal line doesn't change. So let's look at how we take the derivative of some of these polynomials. So this is 3x squared minus 2x plus 3. So the power rule says that when you take the power of your exponent and you multiply it to the front. So when we come over here, right, this says the derivative, so we're going to do it in the derivative column. We start by writing f prime. This is our derivative equation, okay, to differentiate from your function equation. So this is going to be 2 times, right, because it's the power of 2. So you multiply that in the front, 3x. And then for the power, we always subtract 1 from the power to get its new derivative power. So 2 minus 1 is 1. We don't ever have to write a 1 as a power. Okay, and then we move on and we take the derivative of 2x. And the derivative of 2x is just the 2, right? That's the slope of our line. And when we're taking a derivative, we're basically looking for the slope. Okay, and then, of course, the derivative of our constant is 0. So this final derivative equation would be 6x minus 2. Okay, so this would be the equation of our slope. Anytime we wanted to calculate a slope of the tangent line at any x value, we would use this equation to calculate that slope. Okay, so this is the power rule. We take the power, we multiply in the front, and then you subtract 1 from it. Okay, so the derivative f of x is negative 5x cubed plus 2x squared minus 3x. Then the derivative is 3 times minus 5, which is negative 15x to the second power, because you subtract 1 from the exponent, plus 4x to the first power, because you subtract 1 from the exponent, and then minus 3. Okay, so in general, what we're going to do is, let's do this one. This one's kind of different, okay, because we have a negative power, but we still apply the same rule. You multiply the outside, the coefficient, by the power. So negative 1 times negative 2 is positive 2. But then when we subtract 1, we get an exponent of negative 2. So if we start with a negative exponent and you subtract, you get even more negative exponents. So negative 2 times a 3 is a negative 6. So we can technically change this plus into just a minus, right? Subtraction. X to the minus 3. Because when you subtract 1 from negative 2, you get a negative 3. Okay, and then the last thing we would do is we can take these negative powers, right, negative exponents, and write them in the denominators as a positive. Okay, so very rarely do you leave exponents as negatives. Okay, you would move them to the denominator to make them positive. That's one of those properties of exponents you learn in Algebra 1 and in Algebra 2. Okay. So in general, right, if in general, we can come down here. So if this is the derivative, this is your fancy derivative notation. This is our fancy derivative notation, right, of our function with respect to x. It is the power times your base raised to the n minus 1 power. We always subtract 1 from from the power, anytime we do a power rule derivative. Okay, so that's in general. So let's look at some trickier type equations, okay, over here. Where'd it go? Here we are. Here we go. Find the derivative for each of the following. Leave your answers with no negative or rational exponents. So rational means like fractions. So we don't want to have any fractions and we don't want to have any negatives, and write them as a single rational function when applicable. Okay, so the first thing we're going to do is we're going to rewrite this to have only powers. Right? No more fractions if we can. As, not only powers, as no fractions. So we don't want to have any fractions. Which means we have to manipulate this, 2 over x squared. Okay, 2 over x. We're going to change this one to have no fraction. In other words, we're going to bring our x squared to the numerator. So how can we bring our x squared to the numerator? By making the exponent negative. Okay, so we haven't taken a derivative yet, so we're going to leave that as f, 2x to the negative 2 minus 4x cubed. So now let's employ our power rule. We're going to multiply negative 2 by 2. Okay, so first we start by writing f prime, right? We are now taking a derivative, so we write f prime to announce to the world that we are taking a derivative. This is no longer manipulating f, but this is a new thing called f prime. Negative 2 times positive 2 is negative 4. X to the, remember we have to subtract 1 from our power, so negative 2 minus 1 is negative 3. Minus, we're going to multiply our 3 times the 4, right? Your power times the coefficient. 3 times 4 is 12. X, and we're going to subtract 1 from the power. 3 minus 1 is 2. So negative 4x to the minus 3 minus 12x squared. So the last thing we're going to do is we're going to put our negative power back in the denominator, right? It says don't have a negative power in your answer. So we're going to put that back in the denominator, but only that part. The negative 4 stays on top. So negative 4 over x to the positive 3 minus 12x squared. So looking at this one, okay, we're going to use a little fraction trick. So I have 3 terms in the numerator and only 1 term in the denominator. So I'm going to split this into 3 individual fractions, all with the denominator of x. Okay, so I'm going to try and simplify as much as I can algebraically before I do any calculus. So let's split this into 3 different fractions. So all divided by x, just like that. So now let's simplify. 1x will cancel from all of these. So the denominator is gone and leaves me a 3 in the numerator. The denominator is gone, leaves me a 1x. And over here on our last one, the x's completely divide out. So I actually have a nice polynomial, 3x cubed minus 3x minus 2, from which to take the derivative. Okay, so if we can simplify, do some algebra, do some splitting apart, some factoring and some dividing, before we take a derivative, it might make our derivative much, much simpler. 9x squared minus 3 would be our derivative when we do 3 times 3 is 9 to the second power minus 3. Okay, let's see what else we can do. Some algebraic, this problem. Okay, we're going to have to multiply this all out so that we have one polynomial first. Okay, so I'm going to pause the video and do that. You should pause the video and do it also, and we'll come back with your polynomial. Okay, there's your equation in case you needed a little helper. 2x cubed plus 11x squared plus 17x plus 6. So remember, that's still f. We haven't changed our f. 2x cubed plus 11x squared plus 17x plus 6. So now we have a nice polynomial that we can take the derivative of, right, using the power rule. So we write f prime. We are now taking a derivative, so we tell the whole entire world by using the correct notation. So 3 times 2 is 6x to the second power. 2 times 11 is 22x, and then the derivative of x 17 is just 17. There's no derivative of our constant. Okay, sometimes multiplying things out, you have to simplify, right? There's a lot to multiplying things out, doing the algebra to make it easier to take a derivative. Okay, so we're going to employ that same strategy as we did on the one up above. We're going to split this into 2 fractions. So we have those 2 fractions and we have these 2 fractions. So let's split these once again into fractions, and then we'll do some simplifying. So x cubed over x to the 5th minus 5x squared over x to the 5th. So the rule to simplifying these exponents is that we subtract 3 minus 5 and 2 minus 5, right? So we can take them out of the denominator by subtracting them from your numerator power. So x to the 3 minus 5 is x to the minus 2, and x to the 2 minus 5, that's 5x to the minus 3. Okay, so first we simplify your algebraic expression, right? So that we have hopefully just one variable per term, no fractions or nothing like that. So now we can take the derivative. So f prime equals, all right, we bring this to the front. Oh, that's just negative 2x. But the power is now the minus 3 because we subtract 1 from the power. So if we have a negative power to begin with, our power becomes even more negative. And then negative 3 times negative 5 is a plus 15x. And we subtract 1 from the power, giving us a minus 4. So the last thing we're going to do is we're going to take our algebraic simplification and move your negative powers with your variable to the denominator. Okay, we're only going to move the negative powers to the denominator. So that becomes negative 2 over x to the 3rd plus 15 over x to the 4th. Okay, we will learn a rule for this later, right? We're dividing a function by a function, so we can use the quotient rule later. But now we're still going to use the power rule, so we have to do our algebraic simplification. Okay, so we're going to turn our radical into a power. Turn our radical into a power. So this is the 3rd root. The 3rd root. So that means I have a 3rd power. Whatever your root is, that becomes the denominator of your fractional power. And we already have it being squared, so that's going to be the numerator of your fractional power. So the 3rd root of x squared can be written as x to the 2/3. Okay, so the first thing we do is we change your radical into a fractional power. And now we're going to employ that same exponent rule, right? So I can bring my exponent to the numerator by subtracting it from the power that's already there. So now I have an x to the 1st. Okay, so this is 3x to the 1st power, and I'm going to subtract 2/3 from it. Okay, so I have the like bases, so I can add their exponents. So this is 3x to the 1st power, right? There's always a 1 there, even though it's never written. So 3x to the 1st power minus 2/3. So that would be x to the 1/3 power. Okay, which is a much nicer looking thing to take a derivative of. 3x to the 1/3 power. So let's take the derivative. F prime equals, what is 1/3 times 3? That's just 1. So 1x. We don't even have to write a 1 there, but I am just for funsies right now. And then we're going to once again subtract 1 from your power. Okay, we have to subtract 1 when you take the derivative. So I'm going to change my 1 into a 3/3. Okay, if I have a fraction, I want to subtract another fraction from it. So what is 1/3 minus 3/3? Negative 2/3. Okay, so here's my derivative. The derivative is x to the negative 2/3 power. Okay, so my final step is to once again deal with our negative exponent, and we do that by putting it into the denominator. So 1 over x to the positive 2/3. And our last step is to rewrite it as a radical. So this is once again the 3rd root of x squared. Okay, remember the denominator is your power, is your root. So it has a 3 in the denominator, so that's your root. And it has a 2 in the numerator, that is your exponent for your radical. Okay, very nice looking, so nice. These derivatives, once we get them in an easy form, it's much easier. Oh, look at all these fractions, right? Calculus thinks you're brilliant with fractions, so they do a lot of things with fractions. So it's in a nice form, right? It's perfectly natural, so we can just straight take the derivative. There's no algebraic manipulation that we need to do. So what is 3/4 times negative 4? That would be a negative 3, right? The denominators cancel out. 3/4 times 4 is 3. And we subtract 1 from the power. So 3/4 minus 4/4, right? That's 1, is negative 1/4. And now we take care of this second term. 1/4 times 2. 1/4 times 2 is, reduces to 1/2, right? So 1/4 times 2 is 2/4. 2/4 can reduce to 1/2. And once again, we're going to subtract 1 from the 1/4, and that leaves me with a negative 3/4. So negative 3x to the negative 1/4 plus 1/2 x to the negative 3/4. Okay, so I have to once again deal with my negative powers. So hopefully you're getting a good idea of what to do with negative powers. They go into the denominator as a positive power, so x to the positive 1/4 plus, so here we have a numerator of 1 and a denominator of 2. So the 2 is going to go in the denominator with your x. Right? It's already a denominator, so it's basically just getting a friend, x to the 3/4 power. Okay? So anytime we have a fraction, the denominator gets more stuff put in there with it. And our last final step is to deal with our fractional powers again and change them into radicals. Okay, so if this is the 1/4 power, what root am I looking at? The 4th root of x plus 1 over 2. This is the 4th root of x to the 3rd power. Okay, so notice the 2 isn't underneath the radical. Well, the 2 wasn't being raised to a power at all. So the 2 stays out front. Now, had it looked like this, right, if it looked like that, then yes, the 2x would be underneath your radical with it being cubed, but it does not. It is 2 times x to the 3/4. So only the x gets put underneath the radical. Okay, so that's the equation that we would use to find the slope of the line tangent to our graph at any value of x. Okay? Now, sine and cosine, these ones just memorize. The derivative of sine is the cosine of our function, and the derivative of cosine is the negative of the sine of our function. Okay? So sine's derivative is cosine. Cosine's derivative is negative sine. Okay, so just memorize those ones. In fact, let's do one of these problems. Let's do the F. So here this says, find the equation of the tangent line. Okay, we can do all of this before the end of the video. Okay, so F prime of theta, right? Theta is your angle or your variable for angles. 4 times. So what is the derivative of sine? That's cosine. And what's the derivative of your single variable? What's the slope of x? It's going to be a 1, right? There's no coefficient, so you have to think of theta as x, right? Because that's your variable of angles. So the derivative is 4 cosine of theta minus 1. Okay? So if it says we want to write an equation, we need to know 2 things. We need to know the x and the y coordinates, and we need to know the slope. Right? We're going to write it in the equation y minus y1 equals m times x minus x1. Right? That is your point-slope form of a linear equation. That's the one that we use in calculus. So first, we know our x term, right? Here's your x. This is your angle that we're talking about. So that's your x value. That's pi over 2. How do we find the y value that goes along with pi over 2? Well, we plug pi over 2 into your original equation. Okay? That's how we do it. So if we want to find the y value at pi over 2, that's 4 times the sine at pi over 2 minus pi over 2. Interesting. So from your trig, what's the sine at pi over 2? Right, that 90 degrees. The y value is 1. Okay, you need to know your basic trig solution. So the sine at pi over 2 is 1 minus pi over 2. Well, there's not a whole lot we can do with that. So our y value is 4 minus pi over 2. Right, that's your y value. That's going to go right here in a second. Okay, and then the other thing we need, so we have the x value, right? That was pi over 2. We have the y value at 4 minus pi over 2. And now we have to find the slope. And the slope comes from your derivative. So let's plug in pi over 2 into this formula. Okay? If you want to find the slope, we use the derivative formula. So the cosine at pi over 2, what's the x value at 90 degrees? Well, if the sine is 1, that means the cosine has to be 0. So 4 times 0 is 0, means our slope is negative 1. Okay? Very good. So let's put this all together as an equation. Okay, so y minus 4 minus pi over 2, right? That is the y coordinate that we found there in that box. Y minus y1, which is 4 minus pi over 2, equals m, the slope, negative 1, times x minus the x coordinate of pi over 2. Okay, being able to write an equation of a tangent line is a very key skill to have in calculus. Okay, so keep practicing these power rules and these fractions and these radicals and all these other things, and you're going to get good at it eventually. All right? Have a swell day.